On to day 11. What is it this time? Hi and welcome to another episode. And what we've got here is the PiHut Advent Calendar Let It Glow. And we're on day 11. So what's inside? Let's find out. Oh, a ribbon cable of some sort. Oh, it's buttons, isn't it? Get inside the plastic bag. Bang, bang, bang. There we go. Careful though, because ribbon cables, knowing from having a ZX81 and Spectrum, ribbon cables like this are very delicate. We've got some pins as well. So yeah, some more wires, pins, and little keyboard. 1 to 4. I'm assuming we're going to put them inside there because obviously we need to get them onto the breadboard. But let's find out what we have to do. Right, so Let It Glow, Maker Advent Calendar, Day 11, Merry Membrane. Aha, a membrane keyboard. As I say, a ZX81 or a Z80 had these sort of pads. Not much different than what's at ATMs, that sort of thing. Right, we've got Let It Glow, Maker Advent Calendar, Day number 11, Merry Membrane. It's day number 11 of Let It Glow, Maker Advent Calendar. Let's scroll a little bit. There we go. Today we have another control component to play with. The thing in your box today that looks a little bit like the front of an ATM machine. It's a membrane keyboard. That's what this thing is. And this explains the weird title of today's article. Yeah, it does. Right. These flexible friends are a great way to make fun projects with passcodes, program selection and more. And we've chosen this particular 4x1 version as it's much simpler to code than the larger versions. Now, I'm going to have to re-educate you, everybody. This is a 1x4. You talk about how many rows, then the amount of columns. That's how you do it across the whole of the internet in the realms of programming since the days of programming. Even before the days of programming, when it was double bookkeeping. It's 1x4. 1 row, 4 columns. If you don't believe me, go to PiHut's own website and check this particular item and see how they name it. Come on, PiHut, you can do better than this. The box contents, as we know, keypad, extra long header strip, and male-to-male jumper wires. There we go. Right, today's activities. Today we're going to show you how to wire this membrane up to including how the pins are connected, then work some of the programs to make sure the numbers on the front, including the secret present list passcode system. We'll cover some more new topics today, so get your learning hats on. Hats? I've got more than one? That's where I've been going all my life. Right, what is the membrane keyboard? These keyboards are a bit like having 4 regular buttons, but with a singular different approach to the pins. They're compact, thin, and have a handy adhesive backing for the sticking to projects. You know what? I believe it does. We love having these numbered keypads to play with as we can create passcode programs and get our James Bond with our projects. Isn't it Q? Who sorts out the techie stuff, not James Bond. Right, the keyboard has 5 pins, 1 row pin, 4 columns. Exactly, that's why it's 1x4. You don't really need to worry too much about the rows, the columns though, just to consider the row pin is for 3.3 volts that feeds to one side of the keys, and the rest are the GPIO pins to set the inputs and detect the processors. When you press a key that's 3.3 volts, connects to the key pin and sends the high signal to GPIO pin with the content to it, the high being 1, remember? We specifically chose a 1x4 membrane keyboard for the calendar as they're easier to write code and understand, as we can keep the code that drives the simple and familiar. Construct the circuit. As always, make sure the Pico is disconnected from the USB cable working with the circuit. Right. We moved the slider from yesterday, but keep the RGB strand lights in place and we use them with some other today's activities. Okay, so let's slide it across then. Let's not lose the pins. That's the stuff we've got today. We know it's unplugged because basically I unplug at the end of every day. A circuit board should look like this. So all these wires we had plugged in. Oh, not that one. Put that one back. These two wires, this one, and the slider. So we've definitely got everything wired up the correct way, the red, green and grey wires in our case. Fit the keyboard. First fit the 5-pin header to the female socket on the keyboard. It won't go all the way, so don't force it. There's a gap, okay? Won't go all the way, but it did. Literally, it did go all the way. Don't force it if there's a gap. Right, so it went all the way. Next, fit the other side of the header into the breadboard. We've placed ours near to where our slider was, like this. Okay, so it's doing it on this row here, 4th from the left, which is, what row is that? That's row E on the lower board. When we want to put the left pin in, where are we? We count backwards. Pin 27, of course it is. And it goes all the way in. The pins went all the way in on whichever. At least it did on mine. Alright. Now for the wires. You would expect the pins to be in the same order as the keys, but sadly they're not. It can make things a bit confusing when wiring up. Here's a map of the key pins, the GPIO pins we're using for them, and the keyboard keys they relate to. Okay. So keyboard pins, we're counting 1, 2, 3, 4, 5 from the left. The Pico pins, we want 3 volt, 10, 11, 12 and 13. And the keyboard keys are actually 3.3 volts, 2, 1, 4 and 3 for what the pins actually represent. Okay. So we're going to end up looking like this. So the left pin is the physical pin 36, and then 14, 15, 16, 17 for those ones, 2, 3, 4 and 5. Okay, so not too difficult. Let's get another red wire then. We're going from the top row, so A27 comes all the way around to 1, 2, 3, 4, 5. So J5 on the bottom board. Let's start with a blue wire coming from the left. So just the next one along. So A26 is going in pin 14 of A14 on lower board. Okay, so let's find a green wire, pull it off of here. Pin 25, A25, going across to A15. I want a yellow wire. Pin 20, A24, across to A16. Hopefully that's in there. And then it says we need a purple one. We don't have any purple ones, do we? Oh, we do have a purple one. Oh, found it. That did it. Well, it's a pink one, but we'll use a purple one. A23. And get it go in. Being awkward as ever. to A17. That's that. Scroll down some more. Right, fit the block LED. Okay. We'll bring back our trusty block LED from day number 2 as well. We're fitting it in the same place, but with a different GPIO pin, which is follows. Okay. Box number 2. We need the box, what do you call it? The block LED and the resistor. That's what we'll need. We know we need the resistor. So put in the same place. The writing was to the left hand side, wasn't it? No, that's the positive side. So if you remember, the writing went to the left. I'm going to put that in the same place as before. So the left pin, we're putting that in C30. I'm putting the resistor in E30. I can just about get that to go in there. There we go. And we're coming down to G30 on the top board. So all this is on the top board. E30, that's the resistor in. And then we need a light blue wire. Don't think we have a light blue wire, do we? We'll just use a white one. And we'll take that from J30 all the way across to connect the resistor leg to the GPIO 6 physical pin 9, so all the way across to A9, and then we'll take a grey wire and take that from E28 and push that across to the one just to the left of the last one. So that will be, but I'm not wrong. No, I'm doing it right. To the right of that wire, sorry, yeah, to A8. So that last wire was from E28 on the top board to A8 of the lower board, bottom board, right. Definitely got that correct. Yeah, that's on the right hand side, white wires on left hand side. Right. There we go. Right, activity number 1, basic keypad test. Let's run a super simple test to make sure the buttons are registering properly. The script below is set up the column pins as inputs, then start a simple while loop with some if statements to check if they've been pressed. Give this code a try and make sure everything is working properly. Okay. First things first, as always, I always press copy, but they haven't told us yet again, but we need to plug it in first, don't we? So here we go. Let's press the stop button. It's found the Pico. Copy in the code. So let's have a little look at the code first though. Well, we set out the pins, which are a little bit all over the place because they pointed out to us that that's how it is, which is fine. That's how it is. If it is being pressed, it will print out that it's button number 1, and it's going to keep checking every 0.3 of a second. So if we tapped it and let go, might miss it. But anyway, let's press run. Nothing's being pressed. Pick a number. Go on, pick a number from 1 to 4. 3. There we go. It just keeps printing 3 because I'm holding it down. 4, 2, 1. 1, 2, 3, 4. So we know that everything is set up properly. for the keyboard at least. I'll press stop. Activity number 2, LED strand color selector. How about the project to set different colors for the RGB LED strand to use? The keypad allowing us to change the colors whenever we choose. Great for changing the mood of a backlight or a decoration depending on how your day is going. We're basing it on static odds and even code from yesterday. To do this, we're going to introduce something new with functions passing arguments. This is what I said a few days ago. It's possible to do these. So, what is an argument in functions? We've shown in functions before blocks of code that we can call and use in our program whenever we want, handy for things like we might want to repeat. We can pass information in these functions with arguments, which allow us to run some function code but with the argument passed into it. For example, the following basic function sets the color red, but there's no argument here, so we can't change that color each time we call it. So it's always set to red because of the 255 being in the left column was RGB, because this is a proper RGB strip. We can add the argument to the function. We give it a name. Here we're calling it argument color. Notice the stand.fill lines use the same color arguments as the brackets. Fine. Now we call the function, we can add a color we want to the brackets, which means we can change the color each time we call the argument. So my function 255, 0. You can add as many arguments as you want to a function, just separate them by a comma. Our code example below uses 2 arguments to allow each call to provide 2 colors for each of our LEDs. The code. Arguments aside, everything else is the script below should be familiar to you. We have a while loop that looks for button presses, and when the button is pressed, it calls the function and provides it with 2 arguments, color variables. The function runs a for loop, which sets the colors. Then the program watches for more button presses again. We've used key for off, 1, 2, and 3 for different colors. Okay. So we're going to copy this code then. Clicky click click. So let's have a look at this code in action. Again, we've set up the pins. We're telling it which GPIO is for the LEDs. We're telling it how many LEDs we have. So, GPIO number and the LED count, that gets pushed into the strand, equals this, and this. Off is all zeros, green is full on there, blue, white is all the everything, yellows mix and match of red and green. Really? It's not what you expect, is it? Red and green. But that's what it says. But we're playing with light, not paint, you see, this is different. Pink is those, and aqua is that. Again, we're setting the LED index as being 0, because we start counting at 0. Strand, we're filling it as being blank at first. So it's turning all the LEDs off. This makes sense, we should have been doing that from the get-go. As in our older programs, we should have been doing that as well. As soon as we learn how to do that anyway. Functions, blinky 1 is color 1 and 2. And then we're passing the information through. If it's if the LED index is even, it's this, and if it's an odd number, it's this. Use color number 2 instead, so we're going to have 2 different colors. Bit of a delay, blinkety blink, the different colors of what we're doing. So we're going to have it that we send through, if we press 1, we're going to send through aqua and green. Aqua being the first one, so that'll be for the even numbered ones. It'll be aqua, and the odd ones will be green, and then a different set will be white and blue, and we'll have yellow and pink. And then 4, as we know, turns all the LEDs full off. Right, so let's run it. Everything's been set to blank. So what did we say it was going to do? Just to double check. Aqua and green for 1. There we go. Oh, that's a bit bright, isn't it? Oh, you can't really tell. Some of them are green and some of them are aqua. Just very, very bright. Could we bring the brightness down? Not something we've got in the code at the moment, is it? Something you can add to yourself if you want to do it. But anyway, the point is we'll be able to tell I'm changing colours by pressing different buttons. It is doing what's supposed to be in the code, but it's very bright and the camera can't handle it. So let's move on to the other bit. Now I've got Space Invader bright lights in front of my eyes. You know when like someone takes a flash photo of you and you, but can't see now. That's what I'm seeing. So my reading skills are probably even worse than they already are. Right, let's move on. Definitely that one, wasn't it? Yep. That's what we did. Push to flash. Right. The other component we've used with multiple inputs is the DPD switch from day number 5. We ran a program selection example of that. However, the keyboard might be a better choice for certain projects. The dip switch is better suited for something you want to set for a longer period of time. The keyboard is more suitable for things you want to change or control constantly, like colours or speed. We'll create a short, simple script that offers 4 different flash speed levels for our blocky LED via each key. However, we'll use a bunch of while loops instead of if statements, allowing us to create a project that requires a key to be held down to run. It's just another way to play to show you the flexibility of these things. Okay, so the code. Oops. We have a while loop code that runs forever and inside, and we'll have it nested while loops. Each while loop looks for a keypad to be pressed. While it's being pressed, it will set a variable called flash to a different value. We have a function program1 which is then called. It uses the flash variable at this time delay between turning the blocky LED on and off. It's simple as that. Give it a try and hold your finger on one of the keys. Okay, so let's get rid of this, start a new one, copy the code, paste it across, and at this stage I'll say, like I always do, it's a good idea to actually type all these in. Might be a little bit long. If you just want to fly through it, that is up to you, but if you do type it in, it'll make it stick in your head a little bit better over a long period of time. You come back to it and you think, oh yes, that's the bit I'm supposed to be doing here. Seems simple enough, this. They've not bothered to say it, and I know it's just a little blocky one, but I'm going to point it out again. If it turns out you've got photosensitive epilepsy, please be very careful. Maybe not do it at all. I know, realize this is just a little blocky one, but even so, different people have different things that get them triggered. So be careful, but on your own head be it. It has got flashy things happening, so who knows. Right, I'm going to run the code now. So press 1, press and hold it. Not doing anything. Have I plugged things in properly? Oh, that pin's fallen out there. That shouldn't matter though, that's for the LEDs. Okay, a little bit messing around. Realised I've made a mistake myself, and I want to point out to you that it is also why you should double check what you're doing with the wiring, because I'm a noob at doing this as well. I make mistakes, but luckily I've caught it and haven't caused any problems. So before we move on to activity 3, I'm messing around with the LED block, aren't we? Well, I messed up with the wiring. Oops, and I've just knocked this out now. Push that back in again. I messed up with the wiring. Of course, this needs to be up here on E28, not J28 or whatever I plugged it into before. It's E28. It needs to be up near the block. Make sure you've done that right. I was lucky that I didn't run the code and start sending electricity through it and everything. I might have messed things up. So please double check. Let's get on with this. Now we've got the activity 3. The other component we've used with multiple inputs is a dip switch, which we had from day 5. We ran a program selection example with that. However, the keypad might be a better choice for certain projects. The dip switch is better suited for something that you want to set for a longer period of time. The keypad is more suitable for things you want to change or control constantly, like colors or speed. We'll create a short, simple script that offers 4 different flash speed levels for our blocky LED via each key. However, we'll use a bunch of while loops instead of if statements, allowing us to create a project that requires a key to be held down to run. It's just another way to play to show you the flexibility of these things. So let's move on to the code bit of it then. We have a while loop that runs forever, and inside this we'll have a nested while loops. Each while loop looks for a keypad to be pressed, and while it's being pressed it will set the variable called flash to a different value. We have a function, program1, which then is called. It uses the flash variable value as this time delay between turning the block LED on and off. It's as simple as that. Give it a try and then hold your finger on one of the keys. Okay, let's get rid of the old one. Start the new one. Copy the code, paste it in. Run the current script. Hopefully I press a button now. It's not particularly fast flashing. Hold down 2, a bit faster. 3, faster still. It is actually flashing, I don't know if you can see. There we go. Just go back to 1 again to show how slow it was going. There we go, and we can actually look at the program. We know how fast it was going. It was going 1 second, half a second, 0.1 of a second, and 0.05 of a second. Okay. No erroneous input. The last activity required us to hold the button down, but sometimes that's a bad thing. The problem with keypads or buttons when used for a single click input is the risk of the program detecting more than one input if the user holds this finger down for too long. Try it on the first activity and you'll see the program print the same button over and over. Well, we added the short 0.3 delay to debounce the button in that activity, but it's not a perfect solution. There is a method in MicroPython called interrupts that you can use. However, it's a little complicated and we think that might be too much for your first 12 days of coding. Instead, we're going to take a simple approach which we like to use because it's easy to read and understand and works very well. It works. Hopefully. Wait for all low. When we press a key, we send the input pin high. If we keep our finger on the key for too long, the code keeps seeing that high signal and causes multiple presses. What we can do is make our code check that all 4 buttons are depressed, as in low, or 0, or off, before we allow any further entry. We do this by creating a variable to 0 or 1 state and using this in our if statement. It works like this. Take a quick look at the code below first. Okay. So got it down. There we go. Blah, 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 blah. Makes it a bit more confusing doing that. Right. If the state is 0, we allow our if statement to check for the if buttons. If the button is pressed, we set the state to 1. When the state is to 1, as in the button was just pressed, our first if statement can no longer run and check for input. It's set to 0. If the elif, so this is else if statement, will only set the state back to 0 if all 4 keys are set to low, off basically, and the state is 1. Once you take your finger off the key you just pressed, all the keys are now low and the state is 1, allowing the elif statement to run and the setting state back to 1, meaning the first statement is allowed to run again and check for key presses. And they think that's easier than interrupts? Yeah. Anyway, how we check all the keys at low. So there's the code for that. So else if elif state is equal to 1 and key 1 as a value, key 2 as a value, key 2 as a value, blah blah blah. Specifically we're talking about this part. So all the stuff, also there's some more code at the end there. Can't see it because of the copy code, but there's a equal to 0. Okay. It's pretty self-explanatory. You just look at the link together with the equal. Anything you want to check has the same value and they place that desired value at the end. In our statement we want them to alter a value of 0. You can also remove the value which tells the code you want all of them to be the same, but you don't care what the value is like. So you could hold them all down and then it would start doing the code, or you could have all the codes off, all the buttons down, and it would run the code. Anyway, let's get on with running some more code. Paste that and stop run it. So now what's going to happen? So button 1's being pressed. If you notice, hold down 2 now. That's it. I'm holding 2 down, but it's not going button 2, button 2, button 2, button 2, button 2 like it was doing before. And it was the same for 1. That's actually looks like that, but I was keep pressing it. Same with holding 3 down, and the same for holding 4 down. And back for 1 just to prove that. See, it's doing it because I keep pressing it. But if I press 2 a few times and then hold down 1 again, so the code works. Very clever. Right, so we can stop that then. Activity number 5, the secret present list. Shh. This one has quite a lot going on. We'll make the program that asks for a 4-digit passcode from our user and compares what they have entered against the safe passcode. If the passcode is correct, the program prints our secret list of presents. We're using the method above to block the duplicate key presses on this one too. This is a busy code example, so let's outline what it does. Remember, there's usually a few ways to achieve the same thing with code. We've tried to show something that's easy to read, break down and understand, but feel free to comment below with your own scripts and methods. So yeah, comment below or come on my comments and leave them on my YouTube video as well. So we can all play. Right. Our program does the following: creates 2 lists, one containing our passcode, using the variable passcode, and an empty one that will store our button presses, user entry. Checks the length of it, using length, as a user entry list with a while loop. If it's less than 4, the user has not finished keying, so the state is 0. It will check for the next key press. If a key is pressed, we'll use a function to add or append that key to our user entry list. Print an asterisk, which is star, ASCII number 42, and change the state to 1. If it is 4 characters, the user has finished keying, so the while loop is ignored and the code moves on to the if and the else statement below. If the user enters the code matches our passcode, we light the LED and print the list of presents. If not, else, we print the failure message. The program ends after success or failure either way. Let's quickly cover the new things we'll be using as part of the example. Oh dear. Right. Firstly we've got append. Our code starts with an empty list which we will fill with 4 numbers entered by the user. But how do we do this? We use the append method. Our list is called user entry and starts like this. User entry. And then the square bracket, equal square brackets. Because that's what we're looking for. We're looking for something to be entered. To add to the next keyed number, our variable called key, to that list, we will use the line with the format list underscore name dot append bracket thing underscore to underscore add bracket. Our working example looks like this. You can append to any list, empty or not. So there we go. And that is. Now we're checking for the length. So we use the command len. We use len to return the number of items to the list. We simply use len followed by the name of the list in the brackets. We have a while loop that checks the length of our user entry list, like this, to see if the user has keyed in all 4 characters, yet while the length is less than 4. So we have the command while len use entry less than 4. Global variables. Right, in one of our functions we use this line, global state. If you want to change an existing variable inside a function, we have to use global. If we don't, it will consider it a local variable, only part of the function, and won't update it for the rest of our program. So yeah. So I hope that makes sense to the fact that what's the difference between a local variable and what's a global variable. If you're not too sure, come ask in the Discord or come ask in the comments. Print trick. We're using 2 new tricks with our print functions. Okay. End equals quote quote. We use this in our print to make the next print stay on the same line. For example, if we ran the code below the standard print lines, print, open bracket, quote, asterisk, quote, close bracket. Do that a few times, you end up with asterisk, 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 or star, star, star. That's how it would do it. But, however, if we add end, empty quotation marks, after a comma, like this, basically it does this. This output stays the same line, handy for authentic password entry style. So by doing that, what it's sort of doing is stopping new line. If you think of it that way, it's if you were using typewriter, it's stopping it from doing that. It's making it all stay on the same line. But then, though, we can do \n. When we use the \n in front of our string, the text, it creates a new line before the print. So we can force it to do a new line, even though that was happening before anyway. And here's an example by using the \n. So if you actually put \n in it, it will find \n, and then it'll end up with this. It's put a new line in. Now, I'm not going to overcomplicate things, but this can be fun when you've got something you want to print that starts with an N, and you want to put a new line in, or you just put a new, so you sort of like, because you're not really watching what you're doing, you will do \n, and then, as in if you were to do November in lowercase, you'd end up with Ovember, because the N's been done. So obviously what you need is a \n, and then N for November. And then the other thing that can be fun is that when you want to when you actually want to print a \. But as I say, I'm not going to over confuse things. It's just something to think about. Anyway, the code. Have a good read through the code below and all the explanations above, then we'll give it a try. There's a lot of commentary, but you can always delete those lines if you prefer. We'll keep them in. We'll keep them in. Right. Copy the code, stick that in. Press play. Soft reboot. Welcome to the secret present list system. Enter the passcode to continue. What's the passcode? Does anybody know? Is it hiding somewhere in this code? Has anyone decided what it is? Cool. Can't see anything. Does it really matter? Can we just enter any code? Let's do 1, 4, 2, 3. Incorrect password. Access denied. But what's the password? I bet it's in there somewhere. I bet I'm not looking hard enough. Is it just simply set your passcode in a list? 1, 2, 3, 4. Haha, it's there right in front of me. So let's run the program again because it kicked me out because I got it wrong. 1, 2, 3, 4. Haha, I hacked it. Secret present list. So we get a train set, a Furby, a boomerang, and a yo-yo. Okay. That's an interesting combination of things. Right. So that's worked though. You have a look through the code yourself and how that's worked. It's basically self-explanatory after reading everything that we did before. And now day number 11 is complete, and basically it's telling us stuffs of what we've learnt. It does say though, feel free to research interrupts if you're feeling brave. I do actually recommend that if you're getting, you know, a bit of a sweet tooth about programming now. Interrupts is an interesting thing to get your head around. I haven't done it in Python ever, I don't think, but I have done it in other programming languages. It's an interesting one to do. It makes your programs a little bit more robust, I'll put it that way. But you do have to get your head around of what you're actually programming. Anyway, and then it points out tomorrow is the last day. Leave everything where it is and get some rest ready for our final component tomorrow. Have a great evening. Oh, go ahead. Have a great evening after you've played around with us. Have some mince pies already. It's too early, but have one. And if you don't know what a mince pie is, go look it up and see if you can import some, because they're lovely if you get some nice ones. So what we're going to be doing now, we're going to be putting into the comments all the different fancy programming codes that you've done today. Don't forget to look in the description for the Discord and the Patreon links. Go on, have a click, maybe even use them. Don't forget to hit that like, that subscribe button, and definitely that notification bell for the last day tomorrow. But as always, happy gaming.